Okay, this is the notes page for zeros and factors of polynomials. So we have four really important facts that should be reviewed. The first one is if a is a zero of a polynomial, then x minus a must be a factor of p of x. So anytime you want to turn a zero into a factor, it's x minus. 2, if a is a zero of multiplicity m of the polynomial, then x minus a to the nth power must be a factor of p of x. 3, I started mentioning it last video, a polynomial of degree n, as long as it's greater than or equal to 1, has exactly n zeros if a zero of multiplicity m is counted m times. So for example, p of x equals x minus 2 quantity cubed times x plus 1 quantity squared is it's degree 5. So we would expect 5 zeros. But we're going to count the 2 from this factor 3 times. And we're going to count the negative 1 0 2 times. And so if you count their multiplicity, the degree does equal the number of solutions. 4, if the polynomial function p has real coefficients, and if a plus bi is a zero of p, then you got to make the real coefficients pop up. So if one imaginary root is a zero, then its conjugate partner is also a zero. And we won't ever tell you that, so you have to remember that fact there. All right, so let's take a look at several examples, and the directions are what I really want to highlight, because you have to understand what these mean. This one, we want to factor p completely into linear factors. So we don't want the roots, we want the factors. But the way that you do that is very similar. All right, you have to start by seeing if you can factor this, because we don't have any roots. So notice it's 4 terms, and so you're going to use grouping. Okay, so we've learned that before. Remember, grouping means to mentally group these first 2 and the last 2 and pull out the GCF. It's 2 steps. So the GCF of these 2 is x squared. X cubed divided by x squared leaves you with x. Minus 4x squared divided by x squared leaves you with minus 4. That plus comes down. And the GCF of 9x and minus 36 is 9, and that leaves you with x minus 4, and we know we're in good shape because both of those are the same. So then step 2 would be to pull out the GCF of these 2, and they have an x minus 4 in common. So if you divide out the x minus 4, you're left with x squared. If you divide out the x minus 4, you're left with 9. And you might say, okay, that's factored. I've done it. But the directions say factor into linear factors, and this is not linear, that's quadratic. Okay, so this is where it gets a little tricky for students. If a is a zero, then x minus a is a factor. This goes backwards and forwards. If x minus a is a factor, then a is a zero. So what makes this hard is it says to factor, but in order to factor this, we have to take a time out and find the zeros. Okay, because if we can find the zeros, then we can turn them into factors. So we're going to set x squared plus 9 equal to 0 to find the zeros, and we don't need the quadratic formula since there's only an x squared term. And then we take the square root, and you get x is equal to plus or minus. When you take the square root, you got to account for both roots. Pull the I out, so negative under the radical, the square root of negative 9 is plus or minus 3i. So those are the zeros. Okay, but it didn't say find the zeros, it says to factor. Well, how do you turn a zero into a factor? X minus a. So if a is a zero, x minus a is a factor. If 3i is a zero, x minus 3i is a factor. If negative 3i is a zero, then x minus a negative 3i is a factor. So you have to pull and find the zeros, but then you're going to come back and answer the question. And so the factors are x minus 4, and then x squared plus 9 became these two zeros, so that's x minus 3i and x minus a negative 3i, which is x plus 3i. Now we've done it. We have factored this into linear factors with complex coefficients. That just means that it's okay that these coefficients here are imaginary. Okay, so we make sure we answer the question. The next question says find all zeros. Okay, so even though it says find all zeros, you still have to do this the same way. You have to factor with grouping. So we're going to group these two and these two. P of x equals x squared times x minus 3 plus, pull a 25 out, and you're left with x minus 3. Second step for grouping, there is an x minus 3 in common, times you're left with x squared plus 25. So we have now factored this into a linear and quadratic factor, but it says find all zeros. So finding all zeros means you set this equal to 0. So x minus 3 times x squared plus 25 is equal to 0. Well, that means you set each factor equal to 0. X minus 3 equals 0. X squared plus 25 equals 0. So one of your zeros is a real root, 3. And the other two zeros come from x squared equals negative 25. Take the square root and you get x is plus or minus 5i. 1, 2, 3 roots, degree 3. So the number of roots is equal to the degree, if you count for multiplicity. Both of these we factored, but the answers look different. And you can't count it off if you don't demonstrate that you understand the difference between these two directions. Alright, here's a third set of directions. Factor into a product of linear and irreducible quadratic factors. Okay, all that means is that you're going to factor, but you can leave it. If you get a quadratic that doesn't factor over the set of real numbers, you can leave it that way. Okay, there's some debate on how we're going to use that word irreducible, but that's how I'm going to use it. Alright, so we've got a factor. It's 4 terms, so we'll try grouping again. So L of x equals, pull out an x squared, and then you're left with x plus 4. There's that plus. 4x plus 16, the GCF is 4x, and that's good news because then you have the same terms there. So second step in grouping, you pull out the x plus 4, and you're left with x squared plus 4. And to read the directions, we factored it. Factor means write as a product, so that's factored. This is a linear term, and you could factor this over the set of complex numbers, but when we see irreducible quadratic factors, that just means if it doesn't factor with real numbers, just leave it. That's the way we're going to interpret it. Okay, so you're done there. So very important, these three are the three kind of directions that sometimes people get a little confused about. Alright, let's see what else. Alright, next thing, another set of directions, factor Q completely into linear factors with complex coefficients given a graph. So this time we're going to factor, and we need to make sure we go all the way to linear factors, which means you might need to take a time out to find the zeros and then go back and turn them into factors. Okay, now this is different because if you tried to factor this by grouping, you wouldn't get very far. But you're given a graph. And so what you want to do is you want to pull the 0 off of the graph. So if this is an x-intercept right here. X-intercept is 2. Well, that's the same thing as a 0. So we have a 0, 2, which means we have a factor because we can turn all zeros into factors, x minus 2. Okay, so we have one factor. We just need to find the other factors. Okay, so remember what we said this last video. A cool way to factor is to use either long division or synthetic division. So that's what we're going to do. We're factoring with x minus 2. But with synthetic division, you take the variables out. So we're going to put a 2 in the box, and then 1, and then negative 3, and then 3, and then negative 2. And so 1's going to come down, and then 2 times 1 is 2, and then you add to get negative 1. Then 2 times negative 1 is negative 2, and then you add to get 1. 2 times 1 is 2, and then the remainder is 0. So what you've got is the factor x minus 2 and the factor x squared minus x plus 1. So we have factored it, but look at the directions. Are you done? No, that's not a linear factor. So you have to factor that. Well, it doesn't factor. Well, you have to take a time out and you have to go find the zeros. Even though it doesn't say anything about finding the zeros, you have to find the zeros because zeros are really easy to turn into factors, just like we did there. So if we use the quadratic formula, x is equal to negative b, which would be 1, plus or minus the square root of negative 1 quantity squared is 1, minus 4 times 1, all over 2 times 1. So x is equal to 1 plus or minus square root of 1 minus 4 is negative 3 over 2. So the zeros are imaginary. Pull an I out. And we want the exact answer. So negative 1 plus or minus I root 3 over 2 are my zeros. But what are the directions? Factor into linear factors. And how do you turn the roots into factors? You put an x minus in front of them. So this one is going to look like this. X minus 2 times x minus parentheses 1 plus I root 3 over 2, x minus parentheses 1 minus I root 3 over 2. So that's pretty ugly factorization, but that's factoring Q into linear factors. You have to find the zeros first. You have to take a time out to find the zeros. Alright, now the last thing is, can you find a polynomial with integer coefficients that satisfies the given condition? Leave your answer as a product of linear and irreducible quadratic factors. So many people fail to read those directions sometimes and then go farther than they need to go. Okay, so example 1 says R has degree 4 and 0 is 2 and 1 minus 3i. Okay, and so first thing you want to remember is right here, number 4, if polynomial p has real coefficients and a plus bi is a 0 of p, then a minus bi is also a 0 of p. Don't forget the conjugate. So right away you can see 1 minus 3i is a 0, and we've got integer coefficients. Those are real coefficients. So that means that 1 plus 3i is 0. Nobody's going to tell you to remember to do the conjugate on the test. You have to remember that. And we want to write a polynomial with integer coefficients and leave it as a product of linear and irreducible quadratics. Okay, well R has degree 4. So something is going on here. The zeros are 2. You have to turn that into a factor, so that's x minus 2. The zeros are 1 minus 3i, so turn that into a factor. That's x minus 1 minus 3i. And the 0, 1 plus 3i, that's x minus 1 plus 3i. But that's 1, 2, 3 zeros, and the degree is 4. So that's this one. A polynomial of degree n has n zeros if multiplicity is counted m times. So that means we must have x minus 2 must have a multiplicity of 2. And now that works. Okay, but that's not done yet because you want to leave it as a product of irreducible, of linear, which is good, and irreducible quadratic factors. So these are not integer coefficients. So we have to figure out a way to multiply this out. And I've shown you how to do that before when we did the section on complex numbers. But if you printed out the note sheet, it's spelled out here, an easy method to multiply factors of complex coefficients. Remember, you want to distribute the negative, and then you're going to regroup. So x minus 2, put parentheses around the x minus 2, and then all you have to do, since these are the same, a minus bi times a plus bi, all you have to do is multiply x minus 2 times x minus 2 and negative I times I, and then you end up getting rid of the complex number. So let's look at that. Alright, so r of x equals x minus 2 quantity squared. That's fine, and we're going to distribute the negative. That's x minus 1 plus 3i. That's x minus 1 minus 3i. And then we're going to regroup these two. And just by doing that, that makes it a plus bi, a minus bi. So what we're going to do next is multiply x minus 1 times x minus 1, which is square double square. So that's x squared. Multiply those two together and double it. That's minus 2x. Square the negative 1. That's plus 1. And then we're going to multiply 3i times negative 3i. And that gives you negative 9i squared. But I squared is negative 1. So negative 9 times negative 1 is positive 9. So then we have r of x equals x minus 2 quantity squared times x squared minus 2x plus 10. And now we have a linear factor and an irreducible quadratic factor, and they all have integer coefficients. So the imaginaries disappeared. And that's why you have to remember the conjugate. If you don't remember the conjugate, the imaginaries won't disappear. Okay, let's try another one. R has degree 3 with zeros negative 2 and 3 plus 2i, and we want integer coefficients, so don't forget that another root is the conjugate, 3 minus 2i. So r of x is going to turn that negative 2 into a factor, x minus a negative 2, which is x plus 2. Turn that into a factor, that's x minus parentheses 3 plus 2i. Turn that one into a factor, that's x minus 3 minus 2i. It's always x minus, always x minus. The only reason that's a plus is because that was x minus a negative 2. Alright, now we need to fix this up, so we're going to distribute the negative. So that's x minus 3 minus 2i times x minus 3 plus 2i. We're going to regroup. Put the x minus 3's in parentheses, and that gives you the product of a sum and a difference. So you don't have to worry about the outer and inner terms. Just multiply x minus 3 times x minus 3, which is x squared minus 6x plus 9, and then multiply the negative 2i times the positive 2i, and that's minus 4i squared. I squared is a negative 1, so that's plus 4. So your final answer, r of x equals x plus 2 times x squared minus 6x, and then 9 plus 4, positive 13. So there you go with that one. Alright, last example, Q has degree 5 with zeros 4, then I'm telling you the multiplicity is 3, and 2i, that's imaginary. If we want integer coefficients, the complex conjugate pair is also a 0. So that's 3, 4, 5. That's all the zeros we need. So Q of x is going to be, turn that 0 with multiplicity 3 into a factor. That's going to be x minus 4 cubed. Turn that 2i to a factor. That's x minus 2i. Turn that negative 2i into a factor. That's x minus a negative 2i, which is x plus 2i. And this last one is actually easier than that one because you don't have to regroup. All you have to do is recognize that we have a product of a sum and a difference. So the outer and inner terms are going to cancel. So this is going to be Q of x equals x minus 4 cubed. No need to multiply all that out. And then x times x is x squared, and negative 2i times positive 2i is negative 4i squared, but I squared is negative 1. So that's plus 4. And then here, there you have it. And occasionally, again, I'll have students multiply that whole thing out. And you don't need to, because it says leave your answer as a product of linear and irreducible quadratic factors. That's a linear factor. That's a quadratic that does not factor over the set of real numbers, so we're calling it an irreducible quadratic. And that's it for that.